Now we're gonna make this video about the norm of a complex number. Okay, so let's first have let z equals a plus ib with ab reals and I squared is minus 1. Okay, so we can represent this number using the complex plane as the point having coordinates a and b. Okay, so most of the time we are interested in this value, the length of this. This is our z. Okay, so we are interested in the length, okay, between 0 and here. So the length of this one is called the modulus of the complex number z, and it's denoted by z, and its value is given by the square root of z times z bar. Okay, so using the Pythagorean theorem, we can see that z is just a squared plus b squared. Okay, but using this notion of the conjugate, we can see why we have this one. So a z equals a plus ib, z bar is a minus ib, which we said it's the symmetric with respect to the real axis. Okay, so let's do z by z bar. So it's a plus ib times a minus ib, and which is equal to a squared plus b squared. Okay, so now taking the or thinking of this one as positive, z bar is greater or equal than 0. That means it's a real number because it's the sum of two squares, two reals that are in R, so it's real. So that's why we define z as the square root of z times z bar. Okay, so the length here is the square root of a squared plus b squared. Okay, so this is the norm of any complex number. Let's say we have z as 1 plus I square root of 3. So the norm of z in this case is just a, which is 1, plus b, which is the square root of 3. So it's 1 squared plus square root of 3 squared, which is 1 plus 3, which is square root of 4, which is 2. Okay, so in this case we say the norm of the modulus of z is equal to 2. Okay, another thing that we can use in the definition is that what's the norm of minus z. So according to our definition, so this is the square root of minus z times minus z bar, which is equal to z times z bar, and this, according to our definition, is just the norm of z. Okay, so this is our first result. The next one is, what's the norm of z bar? According to our definition, it's z bar times z bar, double z bar. Okay, but z bar, z double bar is just z. Why? Because if this is z bar, you take the symmetric with respect to the real axis again, and you get z. So think of it this way. So it's like flipping it and flipping it back here around this axis, you get z back. So that's why here we have the square root of z times z, which is the modulus of z. So we have proved that the modulus of z is the modulus of minus z is the same thing as the modulus of z bar. Okay? Another thing that we can use here, and it's going to be useful for us, is that we can prove that if the modulus is 0, that means z is 0. Okay? So quick proof is that the modulus of z is 0. That means a squared plus b squared is 0. That means a and b equals 0. That means z, which is equal to a plus b plus ib, equals 0. If we have z is 0, this is simple. If we have z is 0, then its modulus, it's clearly 0. Okay? So remember this result. Z equals 0 if and only if the modulus of z equals 0, if and only if z is 0. Okay? So this is a real number, but this 0 is a complex number. Make sure to pay attention to that. But we have the equivalency here. Another thing that we can use is that we can prove that given any two complex numbers using this concept of modulus. So we go back to the real numbers. We can prove that given any two complex numbers, z1 and z2, then the modulus of z1 plus z2 is less than or equal than z1 plus z2. The modulus of z1 plus the modulus of z2. So this is the triangular inequality. Okay? We can do it using the definition of the norm. Okay? Clearly. So since we have, so what do we know? We know that the norm of z1. Okay, let me have more light here because we don't have enough lights here. So z1 plus z2 norm is just the square root, or make z1 plus z2 times z1 plus z2 the norm, the conjugate. And from here we can prove this result very quickly. Okay? Another thing that we need to note is that we can prove more results concerning the modulus of a number. Okay, we can generalize this result here. We can say that the norm of the sum of zi, I going from 1 to n, is less than the sum of the zi's, the modulus of zi's. So this is a generalization of this one. We're gonna need it somewhat later, but for now, we're gonna prove it later. Or we can use the principle of mathematical induction to prove this result. But for us now, we just see that it's true here, it's true everywhere. Okay? Another thing that we can prove, and we're gonna prove surely, is that the modulus given two numbers, given any two numbers, we're gonna prove that the modulus of z1 times z2 is just the modulus of z1 times the modulus of z2. We'll definitely prove this result since it's very important. We're also gonna prove that the modulus of z1 over z2 is the modulus of z1 over the modulus of z2. Okay? And this will help us in solving many problems where we have to deal with the modulus. Thank you.